Hey there, awesome physics students. Let's talk about some basic wave properties. First of all, remember that all waves come from oscillations. So if we can understand some of the oscillation properties, that will help us a great deal here. We can separate waves into two general categories. Transverse waves, in which the oscillations that cause the waves are perpendicular to the direction that the wave is traveling. So for example, if you have a rope and you give it a flick with your wrist, the oscillation in the rope is going to be up and down like that, but the wave is going to travel in this direction with that velocity. So they're perpendicular to each other. That's a transverse wave. With longitudinal waves, imagine that you had a spring that you were pushing back and forth like this. So the oscillation direction is like that. But in the spring, you would see regions where the string was stretched more and then compressed a bit more and then stretched more and then bunched up a bit more. And the wave in this case, though, is still traveling in this direction, and that's parallel to the direction of the oscillations. An example of longitudinal waves is sound waves. The pressure waves are along the same direction that the wave is propagating, whereas with transverse waves, a good example of that is light wave. Now you know that some of the basic ideas or properties of oscillations, like the period, the time between two oscillations, that will still carry over, and the period of the oscillation that causes the wave will be the period of the wave itself. And similarly, the relationship between period and frequency is an inverse relationship. The frequency of the wave will also be determined by the oscillation frequency. So those will be the same. What other properties can we think about? Well, let's think about if you had a rope, and imagine you gave it a flick and you were sending waves down the length of the rope, but let's pretend that you were actually good at it, unlike what I just showed you. And what we want to do is we want to look at the up and down oscillations of different parts of the string away from its equilibrium position, which would just be a flat string, like a flat string like this. And so this is going to have units up and down of meters. And then we're looking along the length of the string too. That's also going to have units of meters. And we're going to look at the different parts of the wave here. So we see something like this. If we take a picture of this in time, or a snapshot in time, then this is what it's going to look like at any particular point in time. One thing you notice is the distance from one peak to the other peak, and that distance, or the distance between repetitions, is the wavelength, and that's going to have units of meters because it's a distance along this horizontal axis here. And you can take that distance to be peak to peak or trough to trough, that's fine. Or you can do it from, as long as you include both a crest and a trough, an uppy part and a downy part, as they say, then that's fine. Another thing you probably noticed is that there's a height of this wave, and that height, that is the distance from its equilibrium position. So I need to take that from the flat line, the axis here. That distance is called the amplitude, and we use the capital letter A to denote that. Please note that the amplitude is not the peak to trough distance. That is not what it is. It has to go from the equilibrium position to the peak or the trough, for example. Unfortunately, you cannot see the period or the frequency on this graph. If instead we took a look at one particular point on that string and watched it as it went up and down and up and down, and we followed it over time, so we would get like time on the horizontal axis. This would be what's called a history plot. So we're following the history of this one point, and again, we're still following it. The vertical component is, or vertical coordinate here, is still y. That's the distance from its equilibrium position. Then we might see something like this over time. And here we can actually visualize the period. This is the time between oscillations, and this would be again peak to peak, trough to trough. As long as you include one complete oscillation, that's the period. Unfortunately, you cannot visualize the frequency on this graph. Okay, so what's the relationship between the period and the frequency and the velocity? Well, the velocity of the wave is just going to be how far it traveled divided by the time it takes. And in one oscillation, it will travel one wavelength. And the time it takes to travel that one oscillation is 1 period. So the velocity of the wave will just be the wavelength of over the period, or if you use this expression right here, that's just going to be the product of the wavelength and the frequency. And this is regular old, plain old frequency in cycles per second. Okay, now one more thing I need to note is this tells you the relationship between the velocity and the wavelength and the frequency, but this does not determine or control the wave speed. It does not control. And so what I mean by that is that the properties of the medium will actually control the wave speed. This tells you about the love triangle between the velocity, the wavelength, and the frequency. But what happens oftentimes is you'll change the frequency thinking that they will change the velocity, but that just ends up, by changing the frequency, we also change the wavelength in exactly the right way too, that it compensates for that change in the velocity will be the same. That's what I mean by it does not control or determine the velocity. All right?